All right, welcome everybody. So today we're going to be taking some notes over springs and elastic potential energy. So first of all, let's talk about springs and let's talk about Hooke's law. So Hooke's law basically says that the restoring force of a spring is directly proportional to how far the spring has been stretched. And so X here is going to be the displacement of the spring from equilibrium, and Fs is going to be the restoring force of the spring. Now, why do I use the word restoring force? So think about a spring. If I were to pull the spring this way, the force of the spring wants to pull it back to where it was, right? If it started here and I pulled it over that way, the force is going to be going this way. If I started here and I compressed it and I pushed it in, the force is going to be going back this way. So springs always want to restore themselves back to that equilibrium position, back to whatever their natural length was. So in this case, Hooke's law says that those two things are directly proportional. If I pull a spring down with some force X, right, it's going to stretch, if I pull a spring down with some force F, it's going to stretch that spring by some distance X. And if I pull with twice that amount of force, I'm going to stretch it twice as far. That's really what Hooke's law says. Now, because these two things are proportional to each other, we can add a constant of proportionality. A constant of proportionality is just a number that makes an equation out of these two quantities. So I know that the spring force equals how far it's been pulled times some number that goes here, K. And that's going to be called the spring constant. And the spring constant is the same for a given spring. Okay, and all springs could have different numbers. But for one particular given spring, that number doesn't change. Now, you can see Hooke's law this way, where the spring force equals Kx, or you can see a negative Kx. Now, that negative Kx comes from the fact that the restoring force is always opposite the displacement. Again, if I pull it this way, the force is trying to go back that way. Those are two opposite directions. So we would put a negative sign in there to take into account that. Now, we can also, I'm just very briefly going to mention simple harmonic motion. Simple harmonic motion is oscillatory motion under a retarding force proportional to the amount of displacement from an equilibrium position. You're going to have a whole unit on simple harmonic motion later, but we're going to touch on it just a little bit today. So simple harmonic motion occurs whenever I take something and I move it one way, and there's a retarding force, a force going back the other way, trying to bring it back to equilibrium. So if it goes this way, the force pulls back this way, so then it moves that way, and then the force pulls back that way, it moves that way, and force pulls back that way, and back and forth it goes, and it oscillates. Okay, so some common formulas we could use with Hooke's law. So depending on the situation, if you have a vertical spring and something's being hung onto the bottom of the vertical spring, then the weight of the object on the bottom that's stretching the spring could be set equal to the restoring force of the spring. So you could see this a lot, Kx equals mg. Now, if the spring force is the net force, if that's the only force acting on an object, or it's the sum of the forces, then you could set Kx equal to ma. And so you'll see both of those situations pretty commonly. Let's do an example problem here. So I have a load of 50 newtons, so that's a force, attached to a spring hanging vertically, and it stretches the spring by 5 centimeters. The spring is now placed horizontally on a table and stretched 11 centimeters. What force is required to stretch the spring by this amount? Okay, so I start off, I know that if I apply 50 newtons of force, I stretch it 5 centimeters. That's enough information to figure out my spring constant for this particular spring. So 50 newtons, we'll stretch it 0.05 meters. I solve for K. This spring has a spring constant of 1,000 newtons per meter. Now that means this would take 1,000 newtons of force to stretch this spring by 1 meter. So knowing that information, now K is the same for the spring. Even though it's horizontal now and we're stretching it further, K is the same number. The spring constant for this particular spring is still 1,000. So my value of K here of 1,000 times how far I stretch it, 11 centimeters, the new force required would be 110 newtons. So let's look at this from a graphical point of view. So let's say we had this data. So over here in this column, I have the amount that the spring is being stretched. And then in this column, I have how much force it takes to do that. So if I apply 0 newtons of force, I stretch the spring by 0 meters. If I apply 12 newtons of force, I stretch the spring by 0.1 meters. If I apply 24 newtons of force, I stretch the spring by 0.2 meters. Notice if I double the force, I double the displacement. These two things are directly proportional to each other for an ideal spring. So if I plot all these values, I get this. I get a nice linear line. Now remember, on linear graphs, there's really two things we could do. We can find the slope of the graph, or we can find the area under the curve. The slope of the graph is always going to be the y-axis divided by the x-axis. So if I did force divided by displacement, that gives me the slope. The area is related to multiplying these two things. So force times displacement would give me an area here. So in this case, if we look at Hooke's law, the spring force equals kx. If I divide both sides by x, k is the spring force divided by displacement. Hey, this is my y-axis, this is my x-axis, so the slope of this line is going to give me k. So the spring constant in this case is 120 newtons per meter. Now, F versus X graphs. So we've seen force multiplied by displacement before, and that's our definition of work, right? If the force is parallel to the displacement, or if it's in the same direction, F times X gives me the amount of work done, and work is a transfer of energy. So over here on this axis, I've got force. On this axis, I've got displacement. If I find the area of this triangle, it's 1/2 base times height. I'm doing 1/2 force times displacement. This is the amount of work being done on the spring. That's the amount of elastic potential energy stored inside the spring. Okay, so since we store energy when the spring is compressed or elongated, it classifies itself as a type of potential energy, and we're going to call that U of S. So U of S is the amount of energy stored inside a spring, called the elastic potential energy. Okay, so again, we'll look at that graph again. So the graph of a F versus X for a spring that is ideal in nature will always produce a line with a positive linear slope. Now, not all springs are ideal springs. Ideal springs are springs that follow Hooke's law, where the force is directly proportional to the displacement. That means force and displacement would be a linear relationship. If I have any other kind of relationship, if this is a curve of some sort, it's not an ideal spring and it doesn't follow Hooke's law. And there are lots of springs or examples of things that can be stretched that will pull back that don't necessarily follow Hooke's law. Now, we looked at this formula, right? This is the potential energy stored inside a spring. It's going to be 1/2 kx squared. This is on your formula chart. And if we think about it as being the area of this triangle, right? It's 1/2 base times height. Well, the base is the distance x. The height is the force, right? So it'd be 1/2 x times force. And force, according to Hooke's law, equals kx. So I have 1/2 x times kx. That's 1/2 kx squared. Now, as far as conservation of energy in springs, so this is a little bit of simple harmonic motion that we'll talk about today. So if I were to pull this spring up and then let it go, right? So I compress the spring some, and I let it go. The spring is going to drop and then come back up and then drop and then come back up, and it's going to oscillate back and forth. That's simple harmonic motion. Anytime I have an oscillation where the force is always trying to pull it back to equilibrium, right? That's going to be simple harmonic motion. Well, what happens here? Well, when the thing is compressed all the way up here at the peak, all the energy inside of it is potential energy. Then when I let it go, that potential energy turns into kinetic energy as it moves faster and faster and faster. And then it starts, and this is back to the natural length, right? Or back to the equilibrium position. Then as it goes past the equilibrium position, it's stretching the spring again. So that energy is getting converted from kinetic back into potential. So whether it's compressed all the way or stretched all the way, all the energy is potential at those points. Okay, that's all potential energy at the peak and at the valley. Now, as it moves through the equilibrium position right here, as it moves through equilibrium, this is where x is 0, right? This was the natural length of the spring where we started off. So there is no displacement. So there is no potential energy stored there. And all the energy at this point is kinetic. So we compress it, it's all potential, turns into kinetic, turns into potential. Here, somewhere in between the maximum or the minimum and the equilibrium, it's a combination of kinetic and potential. Right? And added together, that's still the total amount of energy that we have. There it's all kinetic again, there it's all potential again, there it's all kinetic again, and so on. So let's do one more example problem. So I have a slingshot consists of a leather cup containing a stone that's pulled back against 2 rubber bands. Now, rubber bands are not ideal springs, but we're going to treat it like they are in this particular problem. It takes a force of 30 newtons to stretch the bands by 1 centimeter. What is the potential energy stored in the bands when a 50-gram stone is placed in the cup and pulled back by 0.2 meters from the equilibrium position? With what speed does it leave the slingshot? Okay, so here's a lot of the math that we're going to have to do here. So first of all, they asked me about the potential energy. Well, potential energy is 1/2 kx squared. And I have an x here. I'm going to pull it back by 0.2 meters. But I don't know what k is. Okay, k was not given to me in the problem. But they did tell me that it takes a force of 30 newtons to stretch it by 1 centimeter. Well, there's a force, there's a displacement. From that information, I can figure out what k is. So the force equals kx. I know the force is 30 newtons. To stretch it by 0.01 meters, solve for K. K is 3,000 newtons per meter. Notice that this was in centimeters. I need to convert that back to meters to get the appropriate units for my spring constant. Now that I know what K is, I can figure out what the potential energy is. So the potential energy is 1/2 kx squared. So here's my 1/2, 0.5, times K, which would be 3,000, times my new displacement, 0.2 meters squared. I store 60 joules of energy. So 60 joules of energy were stored when I stretched that by 0.2 meters. Now we look at the conservation of energy stuff, right? So if I pull it back and I store 60 joules of energy, when I release it, that potential energy gets converted into kinetic, right? And so I'm going to have 60 joules of kinetic energy when the slingshot is released. So I could set that initial energy, my potential, equal to the final energy, which is 1/2 mv squared, the kinetic energy. Plug in the values that I know. U of S here is 60. And the mass I know is 0.05 because it was a 50-gram stone. Solve for V. It's going to be moving at 49 meters a second. Okay, be sure that you get all those notes filled in, any blanks that you may have. And if you have any questions, shoot me an email. Thanks.